Alright, hello everyone. Early morning video. I got work and some stuff to do later, so when I come back in the night, I just want to work on some stuff off YouTube and just, I don't know, just so I can record my video now. Let's see what day we are. I believe we're on the 9th day, if I'm not mistaken. Let's review the channel. Hey, we got some subscribers. Let me share my screen. Not bad, boys, not bad. We were just at 39, we're at 42. So whoever's watching this, thank you. Means a lot. This video is decent. Nice. Yeah, we're on day 9, man. Being consistent. Huge shout out to Noah, cause this is one of my friends that been doing this for a minute. Yeah, just gotta be consistent like him. Yeah, so today we're gonna work on, last night I was fried, man. I was so tired, dude. I couldn't even think, but got some energy now, so hopefully I can lock in a little bit better. But okay, so the logarithmic scale. So in some cases data can span several orders of magnitude, making it difficult to visualize on a linear scale. A logarithmic scale can help by compressing the data so that's easier to understand, making it difficult to visualize on a linear scale. For example, at locked-in we have influencers with follower counts ranging from 1 to 1 trillion. Oh shit! If we want to plot the follower count of each influencer, it would be difficult to see differences between smaller follower counts. We can use logarithmic scale to compress data that's easier to visualize. Okay, with a function log_scale data and base that takes a list of positive integers, list of positive numbers data, and a logarithmic base, and it returns. Hold on, let me tell my brother. Hey, Haas. My bad, guys. So then we're at so positive numbers data and a logarithmic base. And a logarithmic return. Okay, takes a positive numbers data and a logarithmic base, right, and returns a new list with logarithm of each number in the original list using the given base. You may want to use a math.log function. Example: log scale is so it is the data 1, 10, 1000, and 10, and you get 0, 1, 2, 3. Man, it says we gotta use the math.log function, so okay. New list. I guess we were gonna return a list, but the thing is we're gonna have to do an empty, and then we're gonna do for num in data. So we got the number, and now we want to do the math log. Do we have to import math? I'm pretty sure you have to import math, but let's see if it works without doing it. Getting the num math.log num. How do I use the math.log? Because obviously it's going to take in the number and then is it like this? Num and then the base? Oh, okay, we're going to do new list. Oh, shit. X equals that. Then let's just say new list dot append X. And right here we'll return return the new lit. Sorry. Yeah, list. Yeah. It's probably gonna even. Math. Yeah. See. Okay. So we're gonna import math. Come on, boys. Let's go. First try. I'm telling you, I just need some sleep, bro. I'm feeling good. I go way better when you get some sleep. Let's see what he did. X. Exactly the same. Different variables, but nice, man. Nice. Shit, should I start doing my YouTube video in the morning so I get some sleep, man? God damn, it's like I'm in heaven right now with all this light in the background. Hold on, guys. Let me close this real quick, cause god dang. I think this would be good. I'll leave the window open so get some light. Now this is some good lighting right here. Alright, we're gonna do big O notation. I don't know when I gotta go because I gotta eat and then go, but we'll see. So big O notation. There are a lot of existing algorithms. Some are fast and some are slow. Some use lots of memory. It can be hard to decide which algorithm is the best to solve a particular problem. Okay, give me 1 second. I'm not even locked in. Gotta lock in, man. Okay. Alright. There are lots of existing algorithms. Some are fast and some are slow. Some use lots of memory. It can be hard to decide which algorithm is the best to solve. So there are a lot of existing algorithms, right? Some are fast and some are slow. Some use lots of memory. It can be hard to decide which algorithm is the best to solve a particular problem. Big O analysis, pronounced big O, not big zero, is one way to compare practically of algorithms by classifying time complexity. The computer time it takes to run an algorithm, right? We write big O notation like this: O formula. There, where formula describes how an algorithm runtime where space requirements grow as the input size grows. O1 constant. O of log n logarithmic. O of n linear. O of n squared exponential factorial. The following chart shows the growth rate of several different big O categories. The size of the input is shown on the x-axis. How the logarithm will take to complete is shown on the y-axis. So O of n squared is horrible. O of 2. What is this? Exponential. Okay, this is exponential. O of n squared. O of n log n. O of n. O of log n. O of 1. Okay. We got a little video here. 8-minute video? Oh my goodness. That is insane. As the size of input grows, the algorithms became slower to complete, take longer to run. The rate of which they become slower is behind by that big O. For example, O and algorithms slowed down more. Right.
Big O analysis is just a way
Guess
for
we're
us
watching
as
the video.
scientists and programmers to categorize different algorithms by how they slow down as the input size to the algorithm grows. Like, super roughly speaking, it's a way for us to talk about how slow or how fast algorithms can run. And to be very specific, we're worried about the worst case runtime. So, for example, if I pass 100 items into this algorithm and I expect it to take 100 seconds to complete, what's the worst case scenario for when I pass in 10,000 items? How does it get worse as the input size grows? That's what Big O analysis is all about. Take a look at this calculate product function. As input, it takes a list of numbers. And for the sake of argument, this is completely made up, but for the sake of this example, let's pretend that these lines take 2 nanoseconds to execute. And assuming that the list of numbers we pass in has just a single item in it, let's assume that these lines of code, the iteration and multiplication, takes just 1 nanosecond to compute. So we pass one item, say the number 5, into this function, it executes, we get a result. Let's just say that the total there takes 3 nanoseconds. Great. Now what happens if there's 5 items? Well, these lines of code we actually still expect to just take 2 nanoseconds because they don't care about the size of the list that's coming into the function. But if one item took 1 nanosecond, it stands to reason that this iterative loop is now going to loop 5 times and take about 5 times as long, so 5 nanoseconds, leading to a total runtime now of 7 nanoseconds. Great. What happens now if we pass 10,000 items into the function? Well, again, these lines of code will still take about 2 nanoseconds because they don't care about size. But the loop is going to take about 10,000 nanoseconds. So we're talking about a total runtime of 10,002 nanoseconds. So all this to say, this function has a big O categorization of order n, linear time, because the amount of time it takes to run the function is linearly proportional to the input size, the size of the list coming into the function. If 1,000 items takes about 1,000 seconds, 1,000,000 items is going to take about 1,000,000 seconds. Let's take a look at another example. This function, just called length, takes a list object as input. And it's important to understand this is an object because we're just going to assume that this object has a property on it called object size, and that property is just stored in memory, and it's incremented and decremented by other pieces of code whenever we append or pop from the list. The point is it's pre-computed, so our little algorithm here that returns it doesn't have to do any additional math. Now with this function, if we pass in a list with one item, we'd expect just making numbers up here. It's gonna take about 1 nanosecond to return that property back. Great, what happens if there's 100 items in the list? Well, we're just using a static property that's been pre-computed in memory. So it's just taking whatever time it takes to return that field from the function. It's probably just like a memory copy. And so it'll still probably take about 1 nanosecond. If we have 10 million items, again, we're just returning a single number. So it's gonna take about 1 nanosecond. So this algorithm, the time it takes to execute actually is constant no matter what the input size of the list is. So this is order 1 or constant time. It's the fastest big O categorization, or at least the big O categorization that doesn't grow at all as the input size grows. Now let's take a look at this get full names function. It takes 2 lists as input, first names and last names. And we're just going to define n as the length of first names.
Let's see if I understand how this code works. So full names, it's probably adding each other, yeah. For first name and first name, for last name and last names. So it's getting that one and that one. Full names dot append, put f string, boom, boom. Okay. I would have never done that, but return full names, and no, just return the first name
and last name.
So this would take a nanosecond. This would take another nanosecond.
And we're just going to define n as the length of both lists and kind of just assert that both these lists always have the exact same length. It's going to create a new empty list called full names and then iterate over all the first names, and for each first name, iterate over every last name, creating all the possible combinations and returning those combinations from the function. So again, for the sake of argument, we'll just assume that if there's 1 first name and 1 last name, that means there's 1 iteration of both loops, and it will take about 1 nanosecond to return that single combination of first name, last name. But what happens if there's 2 first names and 2 last names?
Shit.
Well, now we're not talking about 2 iterations. We're talking about 2 iterations of the outer loop.
Yeah, so that's gonna be first name, 3. That'll be 6 nanoseconds.
And 2 iterations of
that's 4, sorry.
The inner loop for each iteration of the outer loop. So now it's actually 2 times 2. So we'd expect a total of 4 nanoseconds. And what if we bump n up to 3? 3 first names.
That would be, I see how that would work. Let me think. What is that? That's when you multiply by itself, is that exponential? Oh, what is that? I see how it works now. I was confused in the beginning of how you know that was constant, but now I get it. This, okay, so if it's 3, then you have to multiply by 3. That would be 9. What is the one? Oh, fuck. What is the algorithm that multiplies by itself in big O? Oh, no, man. What is the one that... by itself, yeah. Let me ask you, you have... Motherfucker, just tell me the answer. Oh, exponents. Squared? Exponential? What is this? Oh, it's non-linear. So x squared. Yeah, this is x squared. It has to be x squared. Fuck. I made a mistake. Now if I go back to the video, I have to replay it. Oh, never mind.
Big O analysis is just a way for a list of 4 items, we chop it in half. 10,000. The input size grows. Now let's take a look at this get full names function. It takes 2 lists as input, first names and last names. Possible combination. Loop. Loop. And 2 iterations of the inner loop for each
x squared. What the fuck is you talking about?
So now it's actually 2 times 2. So we expect a total
squared.
of 4 nanoseconds.
Big O
and what if we bump n
up squared?
3 first names and 3 last names. Now we're talking about 3 iterations of the outer loop, and for each iteration of the outer loop, 3 nested iterations. So 9 total iterations, 9 total full names, which means about 9 nanoseconds to run this algorithm. So this one actually gets really slow as we start to increase n. With an n of 100, we're talking about 10,000 total iterations, 10,000 total combinations of full names that we're going to be returning. So you get this kind of parabolic growth in the runtime of the algorithm as the lists get larger and larger. Generally speaking, we try to avoid n-squared algorithms in our code where possible. They can do okay on like really small input sizes, but as the inputs get big, they can get hairy very quickly. Now, I'm not going to show you the code for this one. There's a very famous algorithm called binary search. And basically what it does, in a nutshell, it takes a giant list, let's say 1,000 items, and it's searching for a specific item within the list. And what it can do is at each iteration, chop the list in half. So for a list of 4 items, we'd chop it in half to 2, and then chop it in half to 1, 2 total iterations. A list size of 8, we'd chop it in half to 4, then 2, then 1, 3 total iterations. A list of 16 items, chop it in half to 8, then 4, then 2, then 1, only 4 iterations to handle 16 items. With a list of 1 million items, it would only take about 20 iterations to cut this thing down to size. Logarithmic algorithms grow incredibly slowly. Technically, they're not as fast as constant time algorithms, order 1, which don't grow at all. With a log n algorithm and an input size of 1 million items, we're talking about 20 iterations. Well, if we bump that up to 10 million, we're just talking about a couple more iterations. It really like 22 iterations or something like that. I can't do the math off the top of my head. The point is, these input sizes can get absolutely massive, right? 1 trillion items coming into the list. We're talking about like what, 30 iterations maybe? So for practical purposes, you can think about log n as almost as fast as constant time. And the final complexity class we're going to brush on briefly is the exponential class, or order 2 to the n. These algorithms get so slow so quickly that they're basically never practical for real world use. Even just an n of 15, an input size of 15 items, you're talking about computing out to like 30,000 plus iterations. Once n is 30, you can forget about it. These things will take so long to calculate that it's never going to happen. In fact, cybersecurity actually kind of depends on the fact that some of these algorithms are so slow, because that means you won't be able to try all the possible combinations in a reasonable amount of time. So these are the main complexity classes to worry about. Order 1 or constant is the fastest. Order log n, almost as fast as constant time.
What the hell? What the hell? What just happened? What the fuck just happened?
Depends on the fact that some of these algorithms are so slow, because that means you won't be able to slower than linear time. Technically, you also got order n cubed, order n to the fourth that are even slower, and then exponential time, or order 2 to the n, that is impossibly slow. Even with small numbers of n, your algorithm's going to take so long to run that it's never going to be practical.
Alright, cool. Which of these algorithms tends to run the slowest? O of... No. Okay. Holy shit, we got a little assignment here. So O of n, order n. Let's see what we got going on here. So O of n squared, n squared quiz, O of n m. Classes don't matter. What's the next? Sorting algorithms? What's this? Bubble sort. Holy moly, look how much shit there is. I'm just looking ahead, just curious. Okay. Alright, let's come back here. Alright, let's go till... see till here maybe. See how far I can go, because I might have to go soon, so... order n... O of n, sorry. O of n to order n is very common when the number of steps in an algorithm grows at the same rate as the input size is classified as O of n. So as the input size grows at the same rate as classified as O of n. Okay. For example, our find min algorithm for earlier is O of n. Set minimum to positive infinity for numbers in the list. Compare it to min. If it's smaller, set min to that number. Min is now set to the smallest number. The input to find min algorithm is the list of size of n, because we loop over each item in the input once and we add one step to our algorithm for each item in our list. As we use find min with larger and larger inputs, the length of time it takes to execute the function grows at a steady linear pace. Right. We can reasonably estimate that the time it will take to run based on previous measurement if we find that find min 10 items is 2 milliseconds. Then we can estimate the following. Input size 120, so multiply by 20, I guess. Sorry. 10 multiplied by 10. 10 milliseconds. Yeah, so each 10 items is 2 milliseconds. Assignment. Logged in, we now need to display to our users that the people who follow them with the highest engagement count. This will help them know that which followers they should follow back. Complete the find max function. It should take a list of integers and return the largest value in the list. The runtime complexity, aka big O, of this function should be O of n. So the way I'm thinking is that let's set Damn, how is the infinity and negative infinity in Python? It's inf, but like, do I put negative inf in front of it? Float, there you go. Okay, cool. Float, remember float? Okay. Let's set x to equal float negative inf. So for num and nums, if num is greater than x, if we're gonna do x is equal to num, and then we're gonna return x. Cool. Let me see the solution. Oh shit, you could just put negative in front of the float. Never knew that. Okay, cool. For num and nums. Okay. I never knew this right here. That's why I'm starting to, like, my friend Noah told me to always check the solutions, because you can learn more about what you did and what they did and how you can make it better. Same shit, just negative in front of the float. O of n squared, order n squared. Alright, I'm gonna do this and then I gotta go maybe. O of n squared grows in complexity much more rapidly. That said, for small and medium input sizes, these algorithms can still be useful. A common reason algorithm falls into O of n squared is by using a nested loop where the numbers of... Okay, should we do this? I look-y gotta go. Okay, we're gonna stop right here. I'm probably gonna do this when I come back home. I'm kind of learning a lot. I'm interested. There's a lot to do in this section. There's so much, so we'll see what's going on. Yeah, for today I'm gonna stop right here. Thank you for watching. Whoever's watching this means a lot to me. Yeah. There will be longer videos soon. I just a lot of stuff is going on this week, and I'm doing a little bit of stuff solo. So I'm still doing the YouTube videos, so you guys can see my growth. So if you stick this long, I appreciate you for watching. And yeah, that was day 9. Was it day 9, guys? It's day 9. All right. So yeah. All right, boys. Thank you guys. See you guys tomorrow.